Okay, let's take a look at the mean value theorem for integrals and the average value of a function. So let's kind of write out the mean value theorem for integrals. And I want to point out there's a mean value theorem for derivatives as well, which has something to do with the slope of the tangent line over a closed interval. So you might want to go back and take a look at that and compare it to the mean value theorem for integrals that we're going to look at here. So let's start typing out the mean value theorem for integrals over here, and I'll accompany that with with an illustration. Okay, the mean value theorem for integrals. Okay, so the only assumption we have to make in order to use this theorem is it applies as long as f is a continuous function on the closed interval from a to b. That's it. If the function is continuous on that closed interval, then we can apply the mean value theorem for integrals. So let's draw a picture of some function that's continuous on a closed interval. So I'm going to keep the drawing simple here and look at our picture in the first quadrant. And let's say that our a value is here and our b value is here, and it's continuous on the closed interval. That means there's no breaks from as I draw my graph from a to b. If it'll let me plot these points here without thinking I mean something else. So let's say it starts here at this point and it's a continuous function, maybe does something like this and terminates over here. All right, so that's a continuous function. We'll call this function f. So that satisfies the condition for the mean value theorem for integrals. So if that's true, then what does the mean value theorem tell us? Well, it says there is a c, there is some number c, let's say it that way, there is some number c in the interval from a to b, the closed interval from a to b. Let's make sure this is fitting into the video. There is some c in the interval from a to b such that, and this is the important part, so I'm going to put it on a new line here. If I take f of c and I multiply it by b minus a, which is the width of the interval, the length of the base at the bottom along the x-axis, that's going to equal the integral from a to b of the function f of x dx. Okay? Now that's a lot. That seems like a lot. So let's explore all of the last part after the word then. So let's first understand what the right side of this represents. Well, one way to think about the integral of a function, a definite integral, is it's the area under the curve, okay? So in blue over here, I'm going to sort of draw what we're talking about. I'm sorry, I'm not very good with this tablet. So let's see, let me use a straight line feature. So we're talking about the area under this curve, which looks something like that. The exact area under that curve. That's what the right side is. Let's analyze the left side. The left side says b minus a. Well, that's this distance right here. That's how long that is. If I take b minus a, that gives me this horizontal distance, okay? And what it's telling me is if I multiply that by some y value, some height, right? This is the output of the function, so it's a height, it's a y value. If I multiply that by this height, it should give me the same area that I have underneath the curve. So the key is, see this is a constant, right? Because f of c is a number. So when we think about the left side here, what we want to be thinking about is this is the area of some rectangle. Area of a rectangle. So I need to create a rectangle whose area is the same as what I've got highlighted here in blue. Well, maybe since the base of my rectangle is this distance along the bottom, maybe let's say that this is the height that I want for my rectangle. So if I were to draw my rectangle here, maybe it looks something like that. This area inside the rectangle should equal the area under the curve. And that seems reasonable. One way you can think about this now, when you're talking about there is some number c, well, c is the input to this function where the function has the same height as that rectangle. And if we notice that, that's right here. See, the function intersects the height of this rectangle at that point. So what that means is the c that the mean value theorem guarantees existence of is this input right here. And you can tell, well, the height of this rectangle then is f of c, f of whatever that x value is. And so now, when you look at the area of the rectangle, let's get rid of all these marks inside here. When you look at the area of the rectangle, well, it's the base, b minus a, times the height, which is f of c. That's the area of the rectangle. And the area of the rectangle equals the area under the curve. The mean value theorem guarantees that you can find a c to attain the height you need so that you get a rectangle of the same area. Okay? So that's it. It's pretty simple geometrically to imagine what's going on. Now, just a note here, this f of c, and let me see here, I don't know if that's fitting on the video here, so this is f of c, this height. This f of c is what we call the average value of the function, okay? This f of c, that's a height, right? It's the height of the rectangle. F of c is the average value of the function f. Okay? Sometimes we denote it. Sometimes it's denoted as f subscript AVE, f average, okay? So if you ever want to find the average value of a function, then you have to figure out how high your rectangle is so that that rectangle has the same area as the area under the curve. All right? Now, rather than make a whole new video with an example, let's do that now. Let's practice with this right away to get our bearings, okay? So let's do an example here. Let's say we'll do a couple things. Consider the function, let me see here, I've got my notes. Consider the function f of x equals x squared, right? On the interval from 0 to 3. And we're just going to explore this in lots of ways. So the first part of this question, let's just ask, can we apply the mean value theorem for integrals under these conditions? Okay, so that's the first question. And remember, to use the mean value theorem, you just need a continuous function on the closed interval. Well, we know f of x equals x squared, since it's a polynomial, it's continuous from negative infinity to infinity. So f is continuous on the interval from negative infinity to infinity. So yes, we can apply the mean value theorem on the interval from 0 to 3 because this is a smaller set than negative infinity to infinity, okay? So that's the first thing. Now what are we going to do in the second part? Well, the mean value theorem guarantees that there is a C, remember? So part B is going to be determine all values of C that satisfy the MVT. Okay, so you have to know the mean value theorem. So we know that there is a C in the interval from 0 to 3, right? We know there is because this function meets the criteria to apply the mean value theorem. So now we have to find all of the C values. Now sometimes there may be more than one, but the mean value theorem guarantees at least one. So there might be more. If there are, we'll find them. So here's what we have. We need, now what does C satisfy? We need a C in the interval from 0 to 3, right? Such that f of C times the width of the interval equals the integral from a to b of f of x dx. All right. Now let's plug in everything we know here. Now we don't know C, right? We don't know C. So we're just going to call this f of C. But we do know b. B is 3, right? B is the right endpoint of your interval. So we've got 3 minus A. A is the left endpoint of your interval. So A is 0. We need that to equal the integral from 0 to 3 of f of x, which is x squared dx, okay? All right, so here we go. So we need f of c to make this true. So we have to solve this. We have to solve this for c because we're trying to find all the c values. All right, so let's go ahead and do that. 3 minus 0 is 3. Let's go ahead and divide both sides by 3 to get f of c by itself. Well, that's the same thing as multiplying by 1/3. So I'm going to write 1/3, and I'm going to take that times the integral from 0 to 3 of x squared dx. Okay? So we don't have c by itself, but we'll take it one step at a time. Let's go ahead and evaluate the right-hand side. Again, the way to think of the right-hand side is this is the area under the curve. And here we've divided by the width of that interval from 3 to 0. So we divided by 3. And that should give us the height of our rectangle. Okay? So we have 1/3. The antiderivative of x squared is 1/3 x cubed. And we need to evaluate 1/3 x cubed from 0 to 3. I'm going to factor the 1/3 out and evaluate x cubed from 0 to 3, okay? And that's f of c. So f of c equals 1/9 times, and we're going to plug 3 in. So 3 cubed is 27, minus, now we're going to plug 0 in. 0 cubed is 0. So f of c equals 1/9 times 27, which is just 3. Now before we go any further, because we're trying to solve this for c, let's talk about what this means. F of c is also important. So while we're here, I just want to make a comment. The average height of our function, or the height of that rectangle, so the rectangle height is 3, okay? The rectangle height is 3. That's good to know. And furthermore, the average value of this function is 3. So when we look at this function from 0 to 3, its average output, its average height, is 3. Let's stop for a minute again to draw a picture of what's going on here, because I think connecting it to a picture can help. All right, so let's just sort of illustrate this now. We're looking at the x squared function from 0 to 3, okay? And if I look at, so I'm going to look at f of x equals x squared, right? If x is 0, y is 0 squared. If x is 3, y is 3 squared, which is 9. So that's up here. And we know that this is, sorry, I don't know why it keeps bringing up that menu. And we know that this is a parabola, right? We could plot one, if x is 1, y is 1, if x is 2, y is 4. But basically, it curves like this, right? So we're looking at this guy here. And so if we were to consider the area under this curve, that would be represented by the integral of the function. What we're trying to do here is we're trying to reconstruct the area under this curve with a rectangle that has a constant height. A rectangle that has a constant height. And what we just found is the height of that rectangle is 3. So if this is 9, 3 would be like right there. So now we're looking at, here's our rectangle. The area of this rectangle is equal to the area under the curve. Okay? So this is our average value of the function. That's our average value. Now the other thing is, now we have to find C. Remember what C is. C is any value from 0 to 3 whose output is that average value. So right here, that is where our curve intersects the height of our rectangle. And so our C value is whatever this guy is right there, okay? Okay, so that's where we are. That's what we're trying to find. That's our journey. Now, f of c equals 3. Now don't forget, f of x is x squared. So f of c is c squared. That's key, right? So now if I want to solve for c, all I have to do is take the square root of both sides, and I can see that c could be positive or negative square root of 3. Positive or negative square root of 3. But since the original problem says determine all c values that satisfy the mean value theorem, we only need any c that's between 0 and 3. So in this case, the only c that's between 0 and 3 is the positive square root of 3. And so this c up here in our picture is square root of 3. Now that makes sense because if that's our input to the x squared function, right, if we plug in the square root of 3 to this function and square it, the output is in fact 3. All right, so there's the calculus and the algebra accompanied by a graph to illustrate this. Many times the graph can be pretty difficult. That's one of the reasons the theorem exists. So we can do the calculus and the algebra and not worry so much about seeing it visually, right? You have to be able to graph the function to visualize it. And so sometimes the function is difficult to graph. But we could integrate it perhaps, right? You have to be able to integrate the function. So that is the mean value theorem for integrals, along with the concept of the average value of a function.